Let's take a look at the diagram very briefly. These components have active low inputs, but since the debugging diagram was in active high, we chose to add NOT gates into the reset when we used our own components. 32-bit 1 is the 32-bit multiplexer, and 5-bit 1 is the 5-bit multiplexer, which records the input if the S input is 1. 4 register actually refers to the 32-bit register, which records the data input. 32 adder is our 32-bit adder, which performs our addition of numbers. The control unit takes in the opcodes and produces instructions based on these opcodes. Instructions are then used to control the ALU and switches off and on various multiplexers. This is our ALU, which performs arithmetic and logical operations based on controls sent by the control unit. The 0 output here returns 1 when the output of the ALU are all zeros. The sign extend just takes in inputs and copies the sign bit to make a 32-bit output, while the left shift multiplies the number by 4. The ROM file contains the set of instructions used to run the program. These instructions are used to control address and data values, including the opcodes and functions for the control unit. This is the register file, and this is the RAM file that was provided. The outputs, apart from the 7-segment display, are used only for debugging purposes. This is the display driver. It has an active low reset. This is the clock. When the first 28 bits of the address is 1, the compare 0 block ensures that the last 4 bits of the address are all zeros. The output from this block will then be 1, and this enables the 32-bit register to store the value of the 32-bit data input. The last 24 bits of data value of the data bus input is then shown on the 7-segment display. For simplicity reasons, we will be making our inputs to our data input to be the same as our address data. On the other hand, if the last 4 bits of the address is 0001, the output from the compare 1 block will be 1, and this enables the resettable flip-flop. The resettable flip-flop stores the last bit of the data bus input. If the last bit of data is 1, the NOT gate will turn this to 0, and this switches the 7-segment display off as it disables the 7-segment display. If the last bit of data is 0, the NOT gate turns this into 1, and the 7-segment display shows the value of the data stored in the register above. The output of the 7-segment display will be all 1s, but our 7-segment display is a common anode display, so no segments will light up. To implement this into our processor, we change the constants of the data and address bus inputs into 32-bit address and data bus inputs. So this is our display driver. As you can see, this is the reset. The next 4 switches refers to our address inputs, and the next 4 refers to our data inputs.
Jump uses a label which the hardware does not understand. When the program is assembled, the jump must be converted into a memory address. That memory address is then understandable by the hardware, thus allowing the hardware to perform the jump instruction. Jump, like all other instructions, are fetched into the instruction memory from the program counter, which is here. It is also fetched into the adder where it's increment by 4, which is here. As jump does not require any registers, ALU calculation or memory, no other components are required to be active. Thus, only the jump signal here is set on high, whereas the others like ALU control, registry write, memory write are all set to low. When the assembler converts the label to an address, the most 4 significant bits are stored, and the hardware reused those bits from previous instructions. This happens because the amount of address available dictates that no jump can extend into 4 bits. Now that there are 30 bits, the last 2 bits are stored on the least significant side, meaning that the last 2 bits are a 00 through left shift, which is here. The marks with a high signal, which is here, high signal from the control unit will then allow the address to be loaded into the program counter. This is the branch on equal instruction. The control unit decodes the operation code from the ROM. The control unit will then send a high input to the branch and the ALU operation. There requires to be a high input in the ALU operation, as there needs to be a conditional check. This is specifically when the data in the 2 registers are equal. As these are the only 2 components needed in the branch on equal instructions, the others components will have a low input. The data in the 2 registers from bit 25 to 21 and 20 to 16 needs to be compared. Hence, they are used as the 2 inputs for the ALU. These inputs are used in the ALU and they are subtracted. If the results are 0, which means that they do not match, the project counter is set to project counter increment by 4. This is done through design extend, which is here at bit 15 to 0. It is then multiplied by 4, which is done through the shift left function, which on our project is called left shift. If the 2 inputs are found to be the same, the project counter is just set to be project counter increment by 4. This is the Mars simulator assembly code for the square function. So ST1 is set to 1, ST3 is set to 3, ST4 to 0, and ST5 to 0 as well. Initially, this SW code is to connect to the serial on the FPGA. Addition adds ST1 by 0 increment, and ST5 is equivalent to the addition of ST4 and ST3. After that, ST4 is increment by 2 and ST1 is finally equivalent to the addition of ST1 and ST5. The function is then looped around again to repeat the cycle. If we execute it, we can see the function working, but I am going to comment out the pin function. So yeah, you can see it incrementing over here.
This is the compilation report for our counter program, like inclusive of the processor. We are going to upload it to the FPGA now. And it's completed, and as you can see, it is counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when we reset it, it goes back to 0 and starts again. And 0, and it starts again. This is the square code for the FPGA. So you can see it is counting. Oh, I'm gonna reset it. And 4, 9, 10, 34. Yeah, it is working, so the reset works as well. Reset, and it starts again, and it goes on. 51, 64.